Yo, what's up guys? This is Daryl. Today I'm going to talk about Gödel's incompleteness theorem. Gödel's incompleteness theorem is a very important finding both in mathematics and philosophy. So you will not only change your understanding in mathematics, but also the way you view the world. So why Gödel's incompleteness theorem is so important, and why it is the tomb of Hilbert's program. Let's get started. The story starts from the great mathematician David Hilbert. In response to the previous mathematical crisis, where there were a lot of paradox and inconsistency, Hilbert thought it's just because we didn't have a complete set of axioms. As long as we have a complete set of axioms, and we should be finite, we can construct a perfect mathematical world. So finding the complete set of axioms became Hilbert's dream. In one of the mathematical conferences, Hilbert was about to say, "I have a dream that there will be one day we can find the complete set of axioms by which there will be nothing in mathematics will be unprovable." Anyway, Hilbert just believed that there will be finitely many consistent axioms by which any statement in mathematical world will be proved either to be true or false. However, in another meeting, there was a young man who punched right on the face of Hilbert, proving that Hilbert's program was impossible. And this young man was Godel. So, what did Godel say? Before we start to talk about Gödel's incompleteness theorem, we need to have an idea what a formal system is and what the possible properties a formal system has. A formal system is just a set of axioms. In this system, all theorems are inferred from the set of axioms by a set of rules. There are 4 possible properties in a formal system. They are not necessarily true, just possible. The first one is consistency. It says no theorem of the system contradicts another. What does that mean? For example, there is a theorem saying 1 plus 1 equals to 2. It is impossible that another theorem saying 1 plus 1 only equals to 2. The next one is validity. It says the system's rule of proof never allows false inference from true premises. There is also soundness, says if any formula is a theorem of the system, it is true. These two is kind of relate to each other. Soundness is kind of just saying all axioms are true, because we know all of the theorems are inferred from the axioms, and if there are no rule of proof allowing a false inference from true premises, the theorem must be true. The last one is completeness. It says if a formula is true, it can be proven. Someone might ask here, how is that possible if a formula is true but cannot be proven? If it cannot be proven, how do you know it's true? This is a very good question. We'll talk about it later. Anyway, once we know what a formal system is and what the possible properties the formal system has, we can start to talk about Gödel's incompleteness theorem. Gödel's incompleteness theorem is divided into 2 theorems. The first theorem says any consistent formal system F containing piano arithmetics is incomplete. Do you still remember what completeness means? It says any formula in F is true, it can be proven. So incompleteness just means there are statements in F which can neither to be proved or disproved. Someone might be very confused that what's a statement like if it's neither to be proved or disproved? I'll give you a very simple example. What I'm saying is false. Do you get the idea? If you assume what I'm saying is true, what I'm saying is false. If you assume what I'm saying is false, then what I'm saying is true. Weird, huh? The second incompleteness theorem says, assume F is consistent formalized system, which contains piano arithmetics. Then F cannot prove the consistency of F. Since the first theorem is already very complicated, our main focus will be the first incompleteness theorem today. You might be very curious, what is piano arithmetic? And how is that possible to prove such an abstract statement? How is that related to math? We don't even know how to represent the statement in math. To answer this question, I will introduce piano arithmetic and the two very interesting ideas, Gödel's numbering and diagonalization. Let's keep going. To introduce piano's arithmetic, we need to introduce Robinson's arithmetic first. Robinson's arithmetic is just axioms on natural numbers. It provides a basis for operations on natural numbers. And piano's arithmetic is just a stronger version of Robinson's arithmetic by adding an induction axiom. What is induction? To explain this, I want to take domino as an analogy. As we all know, if we push down the first domino, it will cause a chain reaction to make successive domino down one by one, and finally the whole domino will be down. Induction just takes this idea. If you can prove the first one in the sequence to be true, and if one is true, the next one must be true, you can prove the whole sequence to be true. Why this is important? Because it provides a family of theorems in arithmetic. As long as a theorem satisfies this induction, you don't need to write it down in the arithmetic, because it's automatically included in the arithmetic. So it helps us to remove some redundant theorem in Robinson's arithmetic. I'll give you an example. This is an axiom in Robinson's arithmetic. It says y in natural number either equal to 0 or there exists x, the successor of x equals to y. The successor just means the next number. So let's assume this is not an axiom yet, it's just a statement. So let's start from the first number of natural number. When y equals to 0, obviously it holds for this statement. So let's now consider y, a random y in natural number. If y holds for this statement, now let's consider for the successor of y. So for successor of y, it cannot be equal to 0, and there must be a successor of x equals to successor of y, because that is just y itself. So obviously this statement holds. So that's why we don't need this axiom in piano's arithmetic, because it's already included in the induction axiom. To prove the incompleteness theorem in a mathematical manner, we need to convert the statement into a mathematical representation. Here, we need to use Gödel's numbering. This is a genius idea. It converts each statement in piano arithmetic to a unique natural number. How do we do that? In Gödel's numbering, every element of a statement will be uniquely encoded as a natural number. For example, in our structure, 0 is 1, equal sign is 5, and the natural number is 11 plus this number. It's not necessary for you to use this structure as long as you uniquely encode each element and to be very consistent throughout your proof. Let me give you an example. We have a statement called 1 plus 1 equals to 2. 1 is 12, plus sign is 3, equal sign is 5, and 2 is 13. Now we have a sequence for this statement, which is 12, 3, 5, 13. And there's a fundamental theorem of arithmetic. States that any natural number greater than 1 can be written as a unique product up to the ordering of the factors of prime numbers. What does that mean? It just means for any natural number, there's a unique sequence to describe it. Also, for a sequence, there is a natural number, a unique natural number corresponds it. Here, for our statement, we can write this sequence as a natural number, which is 2 to the power of 12 times 3 to the power of 3 times 5 to the power of 5 times 7 to the power of 13. So this is the unique natural number, the Godel number for our statement. Once we have Godel's numbering, we can utilize it by diagonalization. This is also a very genius idea. The expression of diagonalization is very simple. It says, for any sentence A in a theory T, there exists x such that x equals to the Godel's number of A and A is true. This simple expression leads to a significant theorem. If diagonalization is representable in the theory T, then for any formula B of y, there is some sentence G such that T proves G is equivalent to B of Godel's number of G. The proof is a little bit complicated. I'm not going to talk about it here, but I will show you later why this is so important for proving incompleteness. Now, since we already have Peano's arithmetics, Godel's numbering, and diagonalization, we can start to prove the first incompleteness theorem. Suppose C of y defines the set of Godel's number of theorem. What does define mean? For example, C of y defines x. That just means T proves C of x, and T disproves C of x complement. Then the diagonalization lemma gives us a G where T proves G is equivalent to negation C of the Godel's numbers of G. To be simple, I would just say C of G. Do you still remember the proposition we got from diagonalization? That is, T proves G is equivalent to B of A. Since A is just a sentence in T, so is G. So negation C is just B here. Now let's start proving. Let's suppose T proves G. Because of the equivalence relation, T proves negation C of G. And since T proves G, G is the theorem of T, and C defines the theorem of T. That means T proves C of G. You can see T disproves C of G and proves C of G. That just means C of G is both true and false in T. That means T cannot prove C of G. And also because of the equivalence relation, T cannot prove G. Now let's suppose T cannot prove G. Also because the equivalence relation, T cannot prove negation C of G. And since T cannot prove G, G is not a theorem of T. So since T defines the theorem of T, T disproves C of G. Also because of the equivalence relation, T proves G here. What does that mean? That just means it contradicts each other. So we cannot find a function to decide a statement in T is true or false. That means there will always be some statement in T which is unprovable. So far, we've already done proving Godel's first incompleteness theorem. It implies that we can always find some statements which cannot be proved in a consistent system. So what can we do to these statements? Actually, we can just see them as true because they don't contradict any other theorem or axiom in the system, and we can add them as new axioms. I want to introduce something very interesting here. If you want to prove something math to be true, you can either infer them from axiom or theorem, or you can just prove it to be unprovable. For example, some mathematicians are working on proving Riemann's hypothesis to be unprovable. so that can be true. Weird. Okay, let's go back to our topic. So even if you add a new statement as an axiom in the system, you will still find something unprovable in the system. So this process will go forever and ever and ever. That's why we cannot find finitely many axioms to prove any statement in mathematics. That's also why the incompleteness theorem is the tomb of Hilbert's program. Okay, that's all for today. If you like my video, please give me a like. If you want to watch more, please click the subscription. I will see you next time.